Okay, so we're all seeing these incredible advances in AI models, right? They're getting smarter, faster, more capable every single day. But there's a huge question that we need to tackle. How do we actually get that digital intelligence to work in the physical world? The world of atoms, of steel, of infrastructure. Because the gap between a brilliant AI model and a robot that actually works reliably out in the field, well, that gap is massive. This explainer is all about a new way to think about that gap. We're going to move past the hype to really understand what it takes to build for the physical world.
It all starts with a really simple but powerful analogy. Think about this. The wheel. It was an absolute breakthrough, a fundamental, world-changing invention.
But the wheel by itself didn't revolutionize transportation, did it? No. What did? A moving, stable cart. And that was a complete system. You see the difference? This distinction between the breakthrough component and the valuable system is probably the single most important idea for anyone building intelligent machines today.
So let's just make it official. This is our mental model, the wheel and the cart. Today's AI, all these powerful, amazing models, they are the new wheel, a truly revolutionary component. But they are not the end product. And confusing the component for the system, that is the biggest, most common mistake being made in this entire space.
I get it. The common intuition, the one you see in all the headlines and the flashy demos, is that since AI is getting so cheap and so powerful, building smart robots must be getting easier and easier. It just seems logical, right? But that assumption, as logical as it sounds, is actually profoundly misleading.
And this slide right here gets to the absolute heart of it. Artificial intelligence, that's our wheel. It's the powerful breakthrough component. But physical intelligence, that's the whole vehicle. It's the complete integrated system designed from the ground up for a specific purpose. We've been handed this incredible new wheel. The real work, the real challenge is engineering the entire vehicle around it.
This brings us to a really core problem, something we can call the software thinking fallacy. See, the very mental models that make software developers so incredibly successful in the digital world of bits, well, they become a huge liability when you try to apply them to the physical world of atoms.
This quote says it all. Physical intelligence is not software intelligence with motors attached. This is such a crucial insight. We're not just dealing with code anymore. We're dealing with a fundamentally different class of problem, one that's governed by physics, by material science, by failure modes that a pure software engineer never, ever has to think about.
Just think about it. Software development rewards speed. You can iterate super fast. If something breaks, no big deal. You just roll back the code. Robotics development, though, it punishes all of that. Iteration is painstakingly slow and expensive. Failures aren't just a line of bad code. They are physically destructive. You can't just roll back a cracked gearbox or, worse, an accident that injures someone.
This new reality creates this brutal gauntlet that every new physical system has to run. First, you have the lab. A robot in a lab just proves something is technically possible. Cool. Then you get to the factory floor or a pilot site. There, the robot has to prove it's resilient, that it can take a beating and keep going. But to actually succeed, a robot out in the market has to prove it's profitable. And I'll tell you, most projects die somewhere between that first and third stage.
So why do so many fail? Because the real world is messy. It's totally unforgiving. We're not just talking about the obvious stuff like dust or vibration. We're talking about how those things combine to create nonlinear wear and tear, cascading failures you never predicted. These aren't just little edge cases you can patch later. Nope, they are the baseline, the everyday operating environment, and they will systematically destroy the performance of any isolated AI model you try to drop in.
Okay, so this forces us to ask a really important question. If just putting a smart AI model into a machine is not the answer, then what is the actual product we should be building?
The answer is actually pretty profound. In the physical world, intelligence isn't something you just deploy like you're pushing a software update. It's something that emerges from the entire system working together perfectly in sync. And that leads us to our central thesis, our big idea. The system is the product. True, reliable physical intelligence only comes about when you co-design the entire stack, from the nuts and bolts of the mechanical engineering to the control logic, when you design it all holistically, with those messy, real-world constraints in mind from day one.
And that stack, it is deeply complex. You've got the mechanical design, the electrical systems, all the sensors and actuators, power management, fault tolerance, the list goes on. All of it has to be developed in concert. If you break the tight coupling between any one of these layers, the performance of the whole system can just completely collapse.
So this gives us a really solid working definition. Physical intelligence is the successful coupling of that entire stack. Anything less than that, no matter how cool the demo looks in a lab, isn't a product. It's a research project, period.
All right, so now that we have the framework, now that we understand the problem, where are the real opportunities? Where can we actually apply this systems thinking approach and start building the first, most valuable vehicles of this physical AI era?
The first, and maybe the most durable opportunity zone, is in industrial automation and logistics. We're talking about highly structured environments, where the AI's job isn't some kind of human-level reasoning. Its job is to add insane reliability and handle variability in tasks like assembly, inspection, and moving boxes. Success here is super clear. It's measured in uptime and throughput. That's it.
Next up, we have autonomous systems in these highly constrained domains, like mining, agriculture, and energy. The common thread here is what you might call bounded complexity. The environment is definitely challenging, but it's also predictable in its own way, and the economic incentive to improve safety and squeeze every last drop of productivity out of these incredibly expensive assets, it's just enormous.
Construction and defense are also huge early adopters. Why? Because these sectors will absolutely tolerate a very narrow, specialized solution in exchange for extreme reliability, especially in hazardous or chaotic environments. Even small, incremental gains here can have a massive economic and strategic impact.
And finally, we have medical and life sciences. Now, this isn't about replacing surgeons or scientists. It's about augmenting them, extending human precision and consistency far beyond our natural limits. Yeah, the regulatory hurdles are incredibly high, but that's actually a good thing for builders, because it creates these strong, defensible moats for the companies who are disciplined enough to navigate them successfully.
So when you boil it all down, the real intelligence test in the physical world, it isn't about who can build the slickest model in isolation. It's about who can apply these systems-level principles to create tangible, profitable, real-world value.
The winners in this space, the companies that will still be around in a decade, they won't be the ones promising some general-purpose, do-everything robot. No way. The enduring, truly valuable systems will be the ones that absolutely dominate a very specific economic niche with just an insane amount of focus and engineering discipline.
Look, the opportunity here is it's enormous. It's hard to overstate. But the constraints of the physical world are absolutely unforgiving. And navigating both of those truths, the huge opportunity and the brutal constraints, that is the real intelligence test for this generation of builders and investors.
And that leaves us with one final thought. The new wheel, abundant, powerful AI. It's here. It's in our hands right now. So the real question, the one you should be asking yourself is, what system are you going to build with it?